We'll see a show of hands who's heard about Citrix and specifically Citrix NetScaler. That's fantastic. So Citrix NetScaler, pretty old product for use for load balancing. Probably you touch a NetScaler every day, you hit any major website. The original software-based network device, everything is in software, there's no hardware magic in Citrix NetScaler. It does 40 gigs per second using technology similar to DPDK, which put everything in user space. So the reason I'm here today is I was in a startup called Cloud.com, which resulted in the software called Apache Cloud Stack, which is an alternative to, let's say, OpenStack. And so we got acquired into Citrix. And from there, I was hired into the networking group, the NetScaler group, to help them with get closer to developers, what Gartner calls Mode 2 development, style of development. As I said, the NetScaler is used in very heavy load scenarios, 10 gigabits per second, 40 gigabits per second. But there's nothing that the technology itself prevents you from using it in smaller form factors or smaller or different applications. And so my job in the networking group is to help developers get acquainted with Citrix NetScaler and integrate that into their container and Mode 2 style deployments. Sorry, while we wait for the display to catch up. Here we go. So what I'll talk about is the broad landscape of containers and microservices, and how we're teaching fairly reliable and robust load balancer like Citrix NetScaler new tricks in integrating with containers and microservices. And I've done a bit of study over the past few months on how people are essentially reinventing the load balancer and coming up with new patterns which we are also trying to address. And some of the future directions that we're seeing developers are already adopting or are looking at. And so what's changed is, from the old style of development, is that it's just the rate of change is just exponential, right? And whereas you just had to deploy a few websites, and then now you have to do digital and social and mobile and smart things, and then probably integrate all of them together. And IT is just not able to keep up. They're not able to keep up with that rate of change. And so what we've seen is that two main movements have arisen to address this gap between IT's ability to deliver and the business need to accelerate change. The first is DevOps, and DevOps is not a movement. It's not a title. It's not a job description, but it's more of a movement where developers and operators collaborate more closely. There's a whole lot of automation to make sure that things are repeatable and work every time. And the second movement is the direction towards microservices and containers. And what microservices and containers help you do is is, it allows you to replace your monolithic applications with a bunch of related or fairly independent containers. And what used to be, deploying several monoliths has now become a task of deploying several hundred microservices. And when I talk about microservices versus containers, microservices is the architecture of the application, and containers is how you realize that architecture. And what we have found is that containers are replacing VMs or better than VMs to deliver this style of architecture, mainly because they're not as big, they're easy to deploy, and they're reproducible. And so what you're running on your laptop is reproducible in the data center or in the cloud. And so if you look at what a monolith application looks with with respect to load balancers, typically you have one or maybe a bank of load balancers fronting a set of identical monoliths which are delivering applications. And then application tier talks back to the data tier. Now when you replace that with microservices, it looks more like this, with possibly dozens or hundreds of different microservices all interacting with each other. And so it becomes and this is actually taken from Netflix. This is probably the most visible example of this style of architecture. And so when you look at what it means for load balancing, you had fairly static applications in the monolith. The traffic was mostly from the internet to the application, and if you had to do some changes, it would be fairly at a slow rate, maybe every other week, and you could hand the change set over to a load balancing team, and then they could schedule the change and then make the change when it was appropriate. Whereas when you move to the microservices style, suddenly you have a whole bunch of traffic going across container to container, and what we call east to west container traffic. And not only that, the topology is constantly changing with technologies like continuous integration and continuous deployment. The set of containers that are deployed at any time changes every minute. And so the load balancer suddenly has to keep up at a very fast pace with these changes. And the whole containers and microservices movement is tied together with this mode of development called cloud native development. And that is characterized by things like autoscale, continuous delivery, baked-in resilience. That means that the application doesn't depend on the infrastructure for its resilience. It assumes that the infrastructure is going to fail and then builds that into the application. There's deep monitoring to figure out what went wrong and how to fix it in an automated fashion. And a lot of collaboration between operators and developers. And the implications for this on the container on the networking is that it's very network intensive, because where you have traffic flowing mainly north to south, and you can have optimized that path very well, suddenly you have to worry about communication between microservices, and the network is not reliable, right? And so suddenly you have to, if you're an architect, you have to worry about the reliability, performance, the security. How do you discover the collaborating microservices, and how do you monitor all these microservices? And so if you look at the cloud native landscape in terms of microservices, if you were an architect of an application and you were said, well, I've heard of microservices, they're the greatest thing since sliced bread, I want you to go and do microservices. Suddenly, these are the additional things you got to start worrying about. Not only just load balancing, but throttling, end-to-end encryption. You got to worry about visibility, how to do continuous delivery, how do you manage the lifecycle of these containers, how do you automatically deploy APIs of these microservices.
Can I ask a question?
Sure.
So I know all that headache. So is it worth splitting a monolith application which works well and fine into this, or would you rather you're starting something from scratch, then it makes sense to go for microservices. So would you recommend breaking a monolith application which is deployed in 10 different customers?
Yeah, the main advantage or the main benefit, what people see in moving to the microservices style is the velocity of development. Because each separate microservice can be owned by a team, and that allows them to make changes very rapidly. So if it was a monolith, now they had to wait for the next release train in order to let the changes go through, right? So whereas you are making changes every month or every 2 months because it's such a risky thing, releasing a monolith, now each microservice owner can make a change and release every day or every hour, right? And so that, what I referred to before, that business need of the rate of change, if that is what's driving you, then yeah, I think a microservices methodology makes a lot of sense. And then if you were the infrastructure guy, then you got to worry about a whole bunch more. Now you got to worry about, well, container orchestration, how are these containers isolated? Do I need virtual networks? What if I want to do multi-cloud? Who's going to give me my storage? How do I monitor the network performance? And then this is my bad PowerPoint skills, but yeah, if you were to marry the microservices style and then the infrastructure headaches, that's the smorgasbord that you have to deal with. And so, people say, well, let's use the container cluster manager to solve our headaches. And that's a very good thing to do. So you could use Swarm or Kubernetes or Mesosphere. You have customers using all three. And if you just look at the Google Trends traffic, you would think that Kubernetes is winning over all these. But we have customers, very large customers using Mesosphere, and some customers kicking the tires on Docker Swarm as well. And what they do is they give you an API to orchestrate containers over a cluster of bare metal hosts or VMs. And this enables that DevOps style automation, that velocity that I was talking about. And so what you do is you make a cluster API call, and then it schedules the containers for you, and it should just work. Except they're good for something. So if you want infrastructure independence, you say, well, I don't want to be locked into the EC2 API. Then this is a great thing to do. If you want tight control over your schedulers, that's a great thing that the container managers do for you. Naming and discovery, some of them do it for you, some of them say you got to roll your own. Autoscale, again, partially done a little bit. Security is just a little bit, maybe not enough. And some of them try to do load balancing as well because service discovery and naming is built into it. And when you talk about load balancing, there's two primary kinds. The first is the regular north-south, or what is called ingress in the container land. And so you want to expose your service to the internet, and so that's naturally a load balanced application. And what you would like to say, for instance, that if the URL is XYZ, then send it to that microservice. If the URL is ABC, then send it to that cluster of microservices. And over here, the load balancer doesn't, it's pretty standard. It still has to react to the containers going up and down, scaling out, scaling in. And so what we have built integrations for Citrix NetScaler in the ingress arena here. And then you get the intra-cluster case where you want a load balancer, for instance, from traffic from the microservice beta 1 to the alpha 1 microservice. And you could do it in two ways. You could deploy a load balancer per microservice, or you could deploy a load balancer per node. And we've seen both styles being very popular.
So, Joe,
Go ahead.
I have a question.
Sure.
On the previous slide,
Yeah. This one?
yeah, no.
Yeah, this one,
This
yeah.
one, yeah. So all the traffic going to that URL and that port number will go to all the containers in that particular host? Is that what you're saying there?
No, what I'm saying is that, so the scheduler would have placed the Alpha 1 microservice, for instance, on different hosts, right? And so the load balancer now has to react and say, well, when I get traffic with this URL, I need to send traffic to those hosts on those ports.
So each container has a different parameter?
Typically, if you're deploying in bridge mode, yes, that would be the case, yeah. But then if you used an overlay, then that's a slightly different use case. In which case, each of them would have a separate IP address. Yeah. So sorry if I'm going too fast. You can slow me down. So let me explain this a little bit more. So in the load balancer per endpoint or per service, it's pretty similar to a regular load balancer. You have a microservice trying to talk to another microservice. That second microservice has been scaled out. There's many instances of it, and so you don't want the client to be talking to each of the backend microservices individually. So you put a load balancer in front of it, and that gives you that ability to scale out and scale back in whenever you want without reconfiguring the client. And if you want to do that, there's two styles. One is, sorry, go ahead.
How do you place this load balance as a VM or a load balancer?
Yeah, so in this scenario, typically it's on a containerized load balancer, but you could do the VM as well. So you could do the load balancer per service endpoint, or you could do a load balancer per host. In the second case, what you do is that the services talk to the load balancer on the local host, so they don't have to do any service discovery or anything. All they do is always talk to the local load balancer, and then that load balancer figures out how to send traffic out to the other hosts.
So in the first case, load balancer per endpoint.
Yeah.
If Alpha 1 wants to talk to Beta 1,
Yeah.
it has to go through the load balancer. I didn't understand the rationale for having these two.
So in this case, you get the independence that there's a load balancer dedicated for that service.
Okay.
So that's the advantage of that scenario. But if that load balancer gets killed, then the whole service goes down.
So it's load balancer just for the Alpha 1 service.
Correct, yes.
Okay.
In this case, this is a load balancer per host. And so if Beta 1 wants to talk to Alpha 1, it just talks to its local load balancer. It doesn't try to reach any other load balancer. And so in this case, you get a little more resilience. If the local load balancer goes down, then only that client is affected.
But here in this case, the load balancer deals with all the alphas, Alpha 1, Alpha 2.
Correct, yes.
So if, let's say, Beta 1 wants to talk to any of the alpha services,
That's
it will
right.
have to go through.
The load balancer, that's right, yeah.
Question.
Go ahead.
How do you place these load balances between the containers? Like, how do you sustain between the containers, right? Because when we talked in the previous meetup, it is about all these DPDK, all those things, raise the
That's right, yeah.
And
Yeah,
you bring in load balancer also.
Yeah, in this case, it turns out to be mainly service discovery tricks. So when the client Beta 1 says, I want to talk to Alpha 1, it has to figure out, well, what is the location of Alpha 1? And so typically a service discovery, DNS, something tells it that, hey, if you want to talk to Alpha 1, you better talk to the load balancer. And so it's just a port and IP routing at that point. Go ahead.
So I understand the part about how the load balancer is second example. Like
Yeah.
how load is second and two services traffic, but how is it actually load balanced? Does it form a cluster across all the load balancers? Do you know which one to use?
No, in the right hand case, yeah, in the right hand case, so if Beta 1 and Delta want to talk to Alpha, then they never reach across the hosts to talk to the load balancer. They always talk to the local load balancer. So the local load balancer knows how to get to Alpha 1.
But to do the actual load balancing,
Yeah.
load balancers need to be in sync. They need to have cluster.
Right. So that's where the orchestrator comes in and makes sure that every load balancer is configured with the service information. So let me just discuss that point actually here. So what happens is that the cluster API comes in, somebody's making a change saying that, I either want a new version of the app or scale out this app or whatever, right? And that results in changes in the, let's say, the configuration of the number of instances of alpha or where alpha is placed. So typically, these cluster managers give you this container events that, hey, I did something to the cluster, look at it. And so what you do is that as a load balancer controller, you get these events, and then you react to them and say, well, okay, you told me something has happened. Now tell me exactly what happened. You make a query back to the container management. And then you take that and then you make API calls into the load balancers to reconfigure it. And so whether it's an ingress load balancer or east-west load balancer, the mechanism remains the same, where the cluster manager is key. It manages, or it has the authoritative state of the cluster, and then you use that authoritative state to reconfigure the load balancers.
But containers are very lightweight. They come up and then the lifetime of the container is very small.
Correct. But we're still talking hours rather than not seconds. So
here cluster manager has access to each of the containers on its own, right?
that's right, yeah.
Yeah, but if an external function or something wants to access the containers,
Right,
then they have to go through.
the load balancers.
And the ingress load balancer, is that what is doing that service?
No, the load balancer controller is just a piece of software. It is not in the data path. All it's doing.
No, I'm talking about the ingress.
Oh, the ingress. That's right. Yes. So, as I said, whether it's the ingress LB or the east-west LB, it's the same mechanism. You listen to the cluster manager, you get the stream of events, and then you react to it and reconfigure your load balancers. And so, I worked on CloudStack. I worked on OpenStack. I actually wrote the Hyper-V driver for OpenStack. And so working with these cluster managers is just a pleasure because it's so easy to do these things. And the difference turns out to be between orchestration and choreography. Not very good terms, but this is something that Google uses in their papers. In orchestration, which is what CloudStack and OpenStack tend to do, is there's a set of predefined process. So the process might say, first increase the number of clusters, then call the load balancer, and then do something. And then that means that you have to write some kind of load balancer plugin or driver or something like that, and make sure everything works, and you're able to talk to people, make sure the APIs are good. In the choreography model, the cluster manager says, I don't care what you do, I'm just giving you this event. Do what you want with it. And so your rate of development, the rate of being able to enhance the cluster manager is far more than trying to work with a OpenStack or a CloudStack. But there's slight, whereas the orchestration used to be a little brittle, so if you wanted to do something slightly different, then you have to get agreement with the orchestrator saying that, can I do the orchestration after I configure the network, not before I configure the network? You got to ask that. Whereas when you're doing choreography, you don't have to ask those questions. But then if something goes wrong, you don't know what, it's very hard to debug because you don't know if the network failed to configure or the load balancer failed to configure. But the velocity of development is much faster. So with regards to the ingress and versus the intra-cluster, for the ingress, we have seen people use hardware load balancers in F5 or Netscaler, or in case of cloud, they will use the Google Cloud Load Balancer or Amazon ELB. And these are all proprietary pieces of technology. And you probably pay a lot because you want the performance, you want that feature set. For intra-cluster, it's mostly containerized open source software like HA Proxy and Nginx. And we're seeing newer people or newer software come out open source for example, there's a startup producing something called Linkerd, there's Trafic, and there's Proxy, which is built into Kubernetes, and then Uber themselves have open source something called Hypervan. And the interesting thing is that these are all written in Go language. So what we have done for Netscaler is we already had, as I said, Netscaler is pure software. There's nothing hardware in it, and so the same code is able to run on a dedicated box like what we call the FTX. You can run it as a virtual machine, what we call the VPX, or you can run it on a hypervisor platform, which is optimized to run several different virtual form factor Netscalers. And then we just took the code and then shrunk it down, or not shrunk it down, but managed to make it run in a container. And as I said before, the difference between Netscaler and other load balancers is that it doesn't use sockets, it doesn't use, none of the packets go to the kernel, it's all user space kind of technology. The challenge here for us was that the Netscaler code was based on BSD, and we had to port it to Linux, and that's what took the most amount of time to containerize it. So the other difference is it's proprietary, and there's a control plane that we provide called Management and Analytics System, and that gives you unified monitoring across your hardware form factors, software form factors, and container form factors. And same thing for all this, but the key takeaway is that you get to use the same monitoring and analytics system, management analytics system. You get to keep your investments in your whatever hardware or software you've done with Netscaler, and now it's easy for you to move into containers. And so here are some of the features that may or may not be present in open source. Things like DNS, monitoring and logging, and a different style of API than OSS. Load balancers. Any questions so far? So what you can do is we have a free edition. It's called the Developer Edition, or CPX Express. Unlike any other Netscaler form factor, there's no license required here. There is an end-user license you have to agree to, but other than that, there's no license fee. And it should be available from the Docker App Store shortly, if Docker gets the App Store figured out. And when you want to run it in production, then you can replace it with the licensed version. So the management analytics system, the Netscaler NAS, what we have is a single pane of glass to monitor and manage any number of Netscalers. If you are running CPX, you probably have hundreds of them in your data center or in your cloud. And you get a single pane of glass to manage them. And you don't manage it at a configuration line item by line item, you manage them at an application. You say that for this application, please configure the load balancer for me. So it's a very intuitive and easy to use system. Skip through that. So yeah, it's if you're familiar with CloudFormation, we have something called Stylebooks, which makes it very easy to drive the configuration of a Citrix Netscaler. And then it comes with very nice GUIs and alarms. So if any of your thousands of Netscalers have expired certificates, we'll warn you about it. We'll even bring you some certificates for you. And then you get massive insight through all these Netscalers are streaming data. If you think about it, that every transaction from the internet is going through this Netscaler, you're probably getting tens of thousands of data points per second. We can ingest it all and then give you deep analytics and insights into it. And so what this is showing is that you're getting what looks like a very steady stream of traffic, but our analytic system has managed to flag an anomaly in one of the Netscalers, gives you an alert, and then you can go dig in and find out why that application is not responding. So back to the cluster managers. All of them have built-in load balancers for at least east to west traffic. And I don't know why this says no built-in LV, that's a little old. But all of them do have what is called a layer 4 load balancer. That means it looks at just the TCP header and does load balancing for you. Whereas a more traditional load balancer like Netscaler or HA proxy, Nginx looks at all the way into the HTTP header to do the load balancing for you. And while we were integrating with Kubernetes, we had some challenges. For instance, the ingress load balancer is a virtual form factor or a hardware form factor, whereas the internal network in Kubernetes is an overlay, it's a flannel overlay. And so we had some challenges in integrating that, and I suspect that people who are trying to deploy Kubernetes in the data center would have the same challenges in how do you integrate your software-defined network, which is central to Kubernetes, with the rest of your data center, which is probably not software-defined. And so that's something to be aware of if you guys are looking into Kubernetes. Has anybody deployed Kubernetes here? Or? Okay. But you're deploying. So you typically use VXLAN or Flannel or something like that. And then now you have a challenge of how do you actually get traffic into that overlay network, and how do you get traffic out of the overlay network into the rest of the data center. And so if you use our network ingress controller, you can use the Netscaler to do that for you. Some of the emerging load balancing patterns we're seeing, and some of these are learned from Netflix. You can look at Netflix slide shares to get more details. Client-side LV, I've kind of touched on this. So traditionally what you would do is you would deploy a single load balancer for each application, or maybe one load balancer for several applications. With microservices, that's kind of being inverted. So what you do is you deploy sometimes a load balancer per client. So if you look at, for instance, Netflix Ribbon, it's a piece of software that you compile it with your application, and then it does the service discovery and load balancing for you. And so if you're a client trying to talk to a backend which is scaled to 10 services, you just, the library that you've linked in, the Ribbon library that you've linked in into your application takes care of discovering those 10 endpoints and then load balancing between those 10 endpoints. So it kind of eliminates load balancer, but then you have to write it in Java, you have to write it in Netflix style of writing your application. So if you're writing in Go, or if you're writing in Ruby, Python, then you're out of luck. Or you can take that code and then run it as a process next to your client application. And so then your client application just talks to this one process, what is called a sidecar. And then that sidecar is being reconfigured by the cluster manager. And then that takes care of load balancing the application for you. And this has been very, very popular. As I said, Netflix uses it, Twitter uses it, Linkerd is a product which productized the Twitter product. Airbnb uses it, Uber uses it, and then the Q proxy, which is present in Kubernetes, is a similar pattern we're seeing. So it's an inversion of the traditional load balancing pattern. Very interesting to see. And it has that advantage that you don't depend on that single point of failure, which is the load balancer. So even previously, if the load balancer failed, then you would say, well, what the hell, my whole service went down. So then you had to worry about making the load balancer highly available. You don't have to worry about that here anymore. Another thing is that, again, if you read this very good book called Release It by Michael Nygaard, he talks about this pattern called circuit breaker. So quite often in a microservices environment, you got service A talking to service B, talking to service D, talking to service E. That chain is going on, and then somewhere down the line, one service starts misbehaving, and then that affects all the way back to service A, and then you're scratching your head trying to figure out, well, what the hell happened. And one pattern to deal with that is the circuit breaker pattern, where between each set of calls, insert a circuit breaker, which when it sees a problem, if it sees a problem reoccurring, it opens a circuit breaker, and then it returns a fast failure to the application. And so that fast failure goes back all the way to the originating application, which can deal with it. They're supposed to deal with failures. Or at least you're not seeing slow or buggy behavior in the application. You're seeing something which is more predictable. And what the circuit breaker does is it keeps monitoring that failed application to see if it's come back up. And when it comes back up, it automatically closes the circuit again, and then your traffic is back up again. So it's an automated way of troubleshooting, debugging, and taking care of problems in your infrastructure. And because the load balancer is in the path of all your traffic between microservices, this is one place where you can do it, where you can actually implement this pattern. And we've seen, for instance, Netflix Citrix doing this. Another reliability pattern we've seen is throttling, which, again, you're deploying a microservice-based architecture. There's hundreds of microservices. Somehow you got a loop feeding on itself, and you're DDoSing yourself. And how do you figure this out? How do you prevent it? And so again, inside the load balancer, what you can do is you can put the DDoS protection and then stop that from happening. And chaos monkey is another thing which Netflix has popularized. You want to make sure that your application developers have built-in or baked-in resilience in their application. And so you can start killing things at random and making sure that the application still lives. And one of the things that you can do to cause trouble is to increase the latency or introduce problems in the network. So again, you've got a chain A, B, C, D, E. You start making this link between B and C slow, and then you see, well, what's going to happen? Is my application still responding properly? Is my infrastructure responding properly? And you can find these problems before it happens in production, right? Or you find problems in production and make sure that people fix it before it becomes a real big problem. Continuous integration is as I said, microservices and containers get you that velocity of development. Like each microservices can be changed every hour, every day, whatever, right? But the only way you can do it is that if you do not do manual deploys, you have to deploy automated. So the build chain has to deploy the software into production. And the way people do it is using blue-green or red-black or canary deploys. And the trick is that you deploy the software to a different cluster. And then you tell your load balancer to start routing a small percentage of your traffic to the new cluster, to the new application. And if the new application does not have any problem, then you start ramping up the traffic gradually from 10% to 20% to 30% while you monitor it. And then if there's any problem while you're switching to the new software, then you roll back to the old software. So this gives you what is called a zero downtime deploy. And again, as you can see, that the load balancer is key there because that's what's trying to distribute the traffic between the old and the new application.
So what a canary deploy is like?
It's very similar. So in a canary deploy, what you're doing is let's say you say I want only 10% of the traffic to go there, and maybe you can say that I want only traffic from Canada to go there. I only want traffic from this class of users to go there. And then you make a very careful test. You monitor the canary cluster and make sure there's nothing wrong. And then you start increasing the size of the canary all the way to 100%. Whereas in a blue-green or red-black deploy, you don't. All you do is make sure that the cluster is healthy. You don't really send any traffic to it, and then you switch all the way on at the same time to the new software. So you're taking a bigger chance there, but that's
Canary is more
more gradual.
more more gradual and more reliable.
Yeah. And then you do something called rolling deploys as well, where you don't even bother with this. You just tell the orchestrator that just deploy the new software for me, and it just tick tock, it just starts deploying new software and killing the old software.
And shouldn't it be going from version n to n+1?
That's a rollback I'm showing. Yeah.
Oh, you're showing a rollback.
Yeah, sorry.
I'm just.
So the other things we're seeing that these newer types of load balancers and sidecars and things being used in microservices is that you want to ensure compliance. So your microservices, your application which is PCI compliant, should it be talking to the non-PCI portion of infrastructure? And now, well, guess what? Your load balancer or your sidecar is in the way. It can make sure that it's not doing it. It can enforce those kind of rules. And then for debugging, so you got a vast amount of traffic going between all these microservices. If something is slow or something is going wrong, how do you figure out what went wrong, right? And so there's ways to automatically give you that chain of calls from microservice to microservice with the latency between each call, and then it can tell you which path is taking the longest time. And then there's newer protocols being used in microservices, things like Thrift and protobufs and gRPC, and so it's not just HTTP anymore. And then and so you need more insights into these kinds of protocols as well.
Can you tell a little bit about those protocols?
So Thrift, so HTTP is typical for a REST API. And so typically you send JSON payloads over it, and so you can debug and text it, or they can figure out what's going on. But a lot of people find that to be too slow, that it increases the latency, increases CPU load on their, etc. So they changed to binary protocols like Thrift and protobuf. And so now can the load balancer get you insights? It used to be able to give you insights into, you could say that match this JSON field and do something about it, or match this HTTP header and do something about it. Now suddenly you're sending binary traffic to the load balancer and asking it for insights. And so that's the challenge we're looking at right now. gRPC is nothing but using protobufs with protobufs is a binary protocol from Google. It's like compiling your it's like Sun RPC, but slightly different. It's gRPC is using protobufs with HTTP2, and typically used with the Golang kind of server.
So what's protobuf and?
So protobuf is the RPC mechanism from Google. Thrift is the mechanism from Facebook. They're both binary protocols.
You're basically looking at bit patterns.
Yeah, you have to actually decompile on the fly that this binary blob is actually this data structure, and then I want to match this field of this data structure.
Kind of like Hotman coding.
It's you have to decompile on the fly.
Match.
Yeah, it's challenging. Maybe we can do it, maybe we can't, but that's the network operator will demand it, saying that I need to know what's going on between these microservices. Can you tell?
So that will introduce performance delay.
It could, yes. So yeah, we need techniques to avoid that. Yeah, and then like I was talking, we need streaming analytics from all these network paths to figure out what's going on. I'm going to go very quickly through these things. Some of the future directions we're seeing. When you want to auto scale, typically you're looking at the load of the backend cluster, and then you say, well, this cluster looks heavily loaded. Let me increase the size of the cluster, and that tends to be very reactive. So whereas if you know that Monday morning you're going to get a lot of traffic, why not pre-scale your cluster? And so if you look at the traffic patterns from your load balancer, and you run it through a predictive machine, it can tell you what patterns to follow for your load balancing. Multi-cloud, we have customers who acquire other customers, and then they suddenly say, hey, can you load balance? We got some microservices in AWS, some of them in Azure. How do you deal with it? We haven't dealt with it yet, but that's something that's obviously coming up. Microsegmentation is, typically solved at layer 4. Which microservice is allowed to talk to which microservice. But if you got a load balancer in the path, maybe the load balancer can do that for you as well. And again, between microservices, people generally do not do any authorization or authentication. They just assume that the microservice is allowed to talk to the other microservice. But in this Norton era, I think that's going to change. People are going to start authenticating. They're going to start using SSL between every microservice, even though it's inside their own data center or within their own cloud. And then, once you're in the data path, you can start enforcing policy, who's allowed to talk to what, when and why, and stop it or audit it or do what you want with it. So, to wrap up, load balancing is different for containers and microservices. Containers are being deployed with container cluster managers, and so we have to integrate with those. Hopefully I've showed you that it's a good advantage to use the same technology for your ingress as well as your cross-cluster traffic. And we're seeing that emerging patterns are making the load balancer more important. And what I hope to do is, increase the simplicity or make it more simple, make it more resilient, and future-proof for the network with NetScaler products. Thank you.
Thank you, Chardeep and Kevin, for the wonderful talks. So, if you want to, thank you all for coming, first of all, and if you want to collect the portable battery charger, please do show the completed survey form, and thank you all. Thank you all. And also, I'm over here for some more time, and even Sujata. If you're interested in the T-Labs research engineer position, please do come and meet me or email me your resume at the email facility. Thank you.
Sam. Okay. I did. That's good. Yeah, Sam was telling me a little bit about your yeah, so that's good. Yeah. We don't have actually quite that many going in my group, although other groups might be pushing that, but in ours, it's routinely about well, yeah, it would be interesting to have you guys come over and chat with us at some point, and drop me an email, and then I can see if I can have like our